First of all, I'm finally taking Tateo's suggestion, and I'm setting up playlists instead of having to go to the individual links on the lecture videos. I'm just setting up playlists. Probably what I'll do is just do them by chapter. So it'll say something like, when you go on there, just look for the one that says calculus, chapter 3 or chapter 4 or whatever. And now to do that, I think I can just send you to my page. Is that right? And then the playlist will show up there. Okay, so I'll just put a link to that. Okay, so good enough. I want to take a look today. I'll get you in the lab tomorrow, but I want to move on a little bit and look at a new topic. I want to look at, this is in our book at section 3.9. I think in our book they call it differentials, but it could go by a variety of different names. Differentials or linear approximations or linearization, they all mean the same thing, and I'm not sure which one the other book uses. Probably some combination of those. But here's the idea. Doesn't matter what we call it. Here's the idea. The idea is that if we've got some function, f of x, we can use a linear approximation. Calculus can help us to build a linear approximation of that function that works locally. Okay? And a lot of times it's easier to use a linear function than a curvy function, because curvy functions have more complicated formulas, right? The equations are more difficult that we have to work with. And so if we're trying to get an accurate but quick approximation for the change in this function around some point down here that's maybe this point right here, this, call it f of x, this is some kind of known, convenient place, but we want to know what's going on a little ways away from that. Okay, so this is one of those beautiful things in calculus where we get to just draw a big picture, and there's a lot of these things in calculus. If you can come to understand the picture, then you got the whole thing. Let's kind of fill in the blanks with this. So if we're trying to make an estimate of maybe what's happening right here, okay, we want to know if I scoot over, if I change x by some little amount, how much is y going to change? Well, sometimes we'll trade that exact value for the approximate change if it's close. Okay, so first of all, let's just kind of wrap our brains around. Forget about the blue line. Let's just worry about the function itself. If we call this point right here, this is x, right? Well, let's call this jump right here, this change in x. Let's call that dx, or sometimes we even call it delta x. But because we're going to anticipate using some calculus, we'll call it dx instead. And remember how we kind of think about that. Delta is a macroscopic jump, and dx would be a small jump. But we're going to make these jumps pretty small. So really this is appropriate for us. So then we could say that, isn't that just going to be x plus dx, right? Or x plus delta x, whatever you choose to call it. So then what would the coordinates of this point right here actually be? Okay, so the x coordinate is going to be, x plus dx, or x plus delta x. And the y coordinate is going to be f of that, right? Okay. Now let's go ahead and focus now on so this would be the actual answer. If I wanted to know, if I had some function and I want to know how much the function actually changed when I tweaked x, when I scooted x over dx or delta x, I could just plug that new value into the function and find out. And then I can subtract the two and find out how much the function changed, because sometimes that's what I want to know. I want to know something like, if I extend this out here, how about something like change in y, delta y, equals the difference in those two things. I'm going to run out of space here. F of x plus dx, or delta x minus f of x. Okay, but could also, let's just use that point right there as an approximation, right? So how could we do that? How could we estimate something we'll call dy, which is the approximate change in the function? How could I use the line there to do that? What kind of line would we call that, by the way? It's a tangent line, right? It's a tangent line because look what it does. It touches our function in one spot locally, and at that one spot, what about that line makes it a tangent line? Sure, it touches it in that one spot. Okay, good. The slope of the line is the same as the slope of the curve at that point, right? And we're used to that concept. We dealt with that a lot in previous chapter, right? A little bit in this chapter too. So we know that the slope of the tangent line we could just call f prime of x, which is the same thing as dy dx, right? Change in y over change in x. Okay. So if that's dy and that's dx, that makes sense, right? If I were to solve this for dy then, which is what I'm really trying to find here, isn't dy just equal to, if I take this little equation right here, and I solve for dy, what do I get? Okay, f prime of x. So the derivative of the function times dx. Okay, now that's what we call our differential approximation. That's an estimate of how much the line has, the y value of the line has changed, or the function has changed based on this line, okay? All right, so then the whole point here is to say that the exact change in y is approximated by the differential dy, which we calculate by taking the product of the derivative times whatever dx is, whatever value dx is. Okay, let's look at an example here. This seems a little bit, probably a little strange when you're looking at it all theoretically, but let's look at an example, concrete example. Okay, what if we've got the radius of a ball bearing is 0.7 inches, 7/10 of an inch, plus or minus 1/100 of an inch. Okay, why would there be a plus or minus there? Yeah, there's going to be some error, right? When you build stuff, there's always going to be a little bit of error. It may be small, and hopefully it's small. When you're building something like a ball bearing, depending on the application, if you're just using it as a marble, well, you could probably handle a little bit of error. But if you're using it in, say, a jet engine or something, that the tolerances have to be extremely accurate, or that could spell problems, right? So this is a handy engineering trick then, this differential bit. People use this a lot in engineering. And as we discuss this over, maybe we'll kind of flesh out some of the reasons why it's so handy. It does one thing that's pretty handy. It takes a nonlinear function and it sort of does a quick average of the error on the top side and the bottom side. But I'll get to that later. That's for future reference. So if we were to make a calculation then of the volume of this thing, because let's just say that we know the kind of steel that we use to make the ball bearing, and we want to get an accurate estimate of the mass of this thing, right? So if we know the density of that kind of metal, then we could use the volume to calculate a mass. Maybe that's our reason. Who knows? We're doing this for some reason, though. So volume equals 4/3 pi r cubed. If I just plug in r, then that's going to tell me the calculated volume of this thing, but there's some error associated with it, right? With the measurement of radius. Now, would you agree that when I take into account that error, the calculated volume is going to fluctuate a little bit based on the error? We call that propagated error. I'm going to write that down. Propagated error. And the volume goes as radius cubed, right? And so a change in radius is going to be, in this case, amplified a little bit in the volume calculation because the volume's being cubed, right? So a relatively, does that make sense? Relatively small change in radius when I cube it could end up being a little more substantial. So, so we need to make maybe some estimate of what the propagated error is, right? Now we could calculate it exactly, but let's use this idea of a differential. Okay, so if we've got this volume formula up here, we want to estimate the actual change in volume due to the error. We'll estimate with our differential dV. Now, the only difference here is we got V's instead of F's and R's instead of X's. But what is our differential dV going to look like here, do you suppose? Say it again. Okay, so, but instead of F, we call it V prime of R, right? Because it's what we've really got here. I suppose I should write it this way. What we've actually got, volume is the dependent variable. I'm surprised I didn't do this. I'm usually kind of a stickler about this. And R is the independent variable. And it's nice to write it using functional notation so we remind ourselves of that. This is the dependent variable of the independent variable R, right? Instead of F of X, we have V of R. Input R is to calculate volume V. So dV then is going to be something like V prime of R times dr, yeah, right? Compare that to what we just looked at on the previous page. Okay, the differential dy in this case is equal to the derivative of the function times the incremental movement in the independent variable, dx, right? So the approximate change in the dependent variable equals the derivative of the function times the incremental change in the independent variable, r, dr, right? Now, what do you suppose, we can see what r is, and you know, we can plug in the other parts of v up here, but what's the dr? 100. Does that make sense? Yeah. Because this is the amount, here's the measurement of r, this part right here must be the dr part. That's the little bit of change, potential change in the independent variable r that we're going to input there, right? Okay, so we need to know v prime of r, but that's no big deal, right? We have the volume function right there. So what is v prime of r? Yeah, so if I've got this pi, 4/3 pi, and then I've just got the derivative of r cubed, right? Bring the 3 down, and I get 4 pi r squared, right? And so I could turn this into a formula. dV equals this, 4 pi r squared times dr, right? Okay. So let's plug in the numbers and see what we get. So somebody bust out your calculator, somebody check that, somebody. So 4 times pi times 0.7, and we'll just, you know, as we say in physics, we'll just suppress the units here, which is just a cop-out way of being lazy. But we know we're dealing with distances in inches, right? And so therefore volumes would be in what units? Inches cubed. Yeah, cubic inches or inches cubed, right? So 0.7 squared times dr. Now the dr, what about the dr? It says plus or minus 0.01.
Well, the change is the same.
So okay, in the line it's going to be the same, isn't it?
Yeah.
Because if we've got a linear function and we go forward by a certain amount or backward by the same amount, the line's going to change by the same absolute amount. In this case, because the slope is positive, if I go forward, dy is positive. If I go backward, dy is negative, right? But I could go ahead, this is kind of slick, I could go ahead and just attach that plus or minus as the dr, right? So the dr becomes times plus or, that's a times, right? We're not actually adding or subtracting. times plus or minus 0.01. And my answer then is going to inherit that plus or minus feature, which makes sense, right? I'm going to get an answer, dV equals plus or minus some number. 0.062. Okay, so we get dV equals plus or minus 0.062 cubic inches, right? If we put the units in there. Okay, make sense? And that, once again, that really does make sense for us, because if we look at, and here's actually, I've got a little graph of what a volume function looks like. You know, this is a graph of 4/3 pi r cubed. If I pick some point and I make this linearization, well, yeah, if I move, you know, the volume's going to change. If I go forward, it's going to get bigger. Excuse me, the radius. If I back the radius off a little bit, if the actual measurement was a little bit smaller than what we measured, then it's going to shrink a little bit. So the plus or minus makes sense. The volume could be bigger than or less than our target value, because the error in the radius could be bigger or smaller. Okay? So, are you sure about that calculation there?
I don't know. It was supposed to be.
Did you square?
0.7? Yeah. Yeah, I got it.
You got the same thing? You're kidding.
We do it with.
Well, maybe I did it wrong. I have it down as 0.01437, but that's not right.
It was the same thing.
You guys all got the same thing? Okay. I'll believe you. Okay. That's good. I don't know what I did. I screwed something up, but oh well. Okay, so now that's not bad, I guess. But how do we know if that's acceptable or not? Does that mean anything in absolute terms to you? If I just tell you out of the blue that the error in volume, and propagated error here, the error in calculated volume is plus or minus 0.062 cubic inches. Intrinsically, does that mean anything, that number? It sounds kind of small. And I guess it depends on what you're measuring, right? I mean, if I were to say something like, I'm going to make a linear measurement, and the error in linear measurement is, let's say, I'm just taking something kind of abstract and unrelated here. Let's say I get the measurement to plus or minus 1 inch. Is that good or bad? Sure. I mean, that's pretty bad if I'm measuring the width of a desk. Plus or minus 1 inches, that's a lot of error. But if I'm measuring the circumference of the Earth, well, shoot, I mean, that's probably pretty good, right? Now, so the difference here is in the comparison to the value of in this case, V, right? So this number by itself is pretty meaningless. But if I could somehow find a way to compare that to the actual volume calculation, then we could tell if we're on track or not, right? And the way we do that in math or science is by using something called relative error. Now, you've probably made some preliminary forays into relative error in your science classes, but we're going to step up the game just a little bit here with relative error. Okay, so with relative error, but the good news is this is a lot easier way to handle it too. Relative error, in this case, we'll take the the example of the volume stuff we're working with. Relative error would equal, in this case, dV divided by V. That's all we have to do, right? We're just going to divide the differential propagated error calculation by the actual volume, and then we'll get some idea if it's really any good, right? Because we would have found, for example, if we did that plus or minus 1 inch linear measurement error, plus or minus 1 inch out of 24 inches is not good. But plus or minus 1 inch out of how many, I'm not going to take the time to figure it out, but however many billions of inches it is to go around the planet, darn good, right? So if we were to plug these numbers in, then I get dV is plus or minus 0.062 over, real quick, let's make a volume calculation. What is V of 0.7? What is that? 1.44? Okay, cubic inches. So now we can get an idea if that's really any good. If I take the quotient of those two things, what do I get? Okay, so I get plus or minus 0.04, right? Now that means something, because are there any units to this, by the way? Ah, they're going to cancel, aren't they? Yeah, if I look at the units here, I've got, oops, I've got inches cubed over inches cubed, right? Because the differential, the change in volume is measured in cubic inches, and the volume itself is measured in cubic inches. And so this is good. This is another thing that as you kind of work your way through math and science classes, you'll come to appreciate the beauty of unitless quantities. Unitless quantities are great because they really stand on their own a lot better, right? We can scale things up and down, and later in the year I'm gonna show you an example of this kind of outside of the realm of calculus. That's really cool. It's a physics deal. It really helps you appreciate why we like to have these unitless quantities in physics rather than quantities with units if possible. So this 0.04 has no units. What does it mean? It's a measure of it's like a size comparison, right? So 0.04, could we find a better way to think of that? Well, maybe we could make it a percentage, right? What if I just slid the decimal over two places? Isn't that the same thing as plus or minus 4%? Now that means something, right? Now that we all know that means something. 4%, we all can get an idea. 4%, well, that's okay. I mean, maybe that's good enough, maybe it's not, but now at least we know, right? Okay, there's even a better trick with this, though. That was still quite a bit of calculating to do. I had to make two relatively big calculations to find this answer. I had to calculate dV, right, and V. But I could be even a little trickier than that. Okay, watch this. This is a great trick. So we said that V equals 4/3 pi r cubed, and you already told me, I'm just rewriting this, so you told me then that dV equals 4 pi r squared dr, right? Relative error equals dV over V. Can you think of a trick to make this calculation even easier? Before I start plugging numbers in and calculating quantities? Why not do some algebraic cancellation here, some simplification? Why not write this as 4 pi r squared dr over 4/3 pi r cubed? A lot of cancellation there, right? Look at this. The pi's go away. I can cancel all but one r. And 4 divided by 4/3 is what? 3. Yeah. So my answer then is just 3 dr over r. That's pretty simple, right? Now to find the relative error, I just have to plug in that stuff. So relative error then is roughly equal to 3 times plus or minus 0.01, because that was our dr, right? Divided by r, which was 0.7. How about that? That's pretty easy. So then we get plus or minus 0.03 over 0.7. That's the same as plus or minus 3/70. Did I do my math right? Does that make sense? Here, let me not skip that step.
Oh, yeah, yeah. Oh, you're good.
Are we good?
Yeah, yeah.
Okay. Right? And that's pretty good. Okay. That's telling me that's a pretty accurate estimate. Okay. Now, if we go back and we look at, so I guess I need to make maybe one more point here on this little idea. Because this thing is nonlinear, I'm just going to do this qualitatively. Would you agree that the blue volume function is getting steeper as R increases.
Yeah.
Right? So would you anticipate then, now think about this a little bit, we had this plus or minus 0.01, which was our error measurement in the radius, is the top side of that. So let's just say that it's actually that we're off, that we're too small, that the actual measurement is actually 0.71 instead of 0.7. Compare that situation to if our value is a little too big. It's actually, in reality, we find out it's 0.69 instead of 0.7. Are those going to have equal effects on the volume? Those errors, the top error or the bottom error? Okay, it's getting steeper above, meaning for values of R bigger than 0.7, right? So would you agree that a small step to the right here is going to give us a larger vertical step?
Sure.
It's going to have a more profound impact on the propagated error than it would if I step backwards because it's flattening out to the left. Okay, and so if I were to calculate, that even complicates matters worse because now if I wanted to do an actual calculation of propagated error, I have to have two different numbers, one on the bottom and one on the top, each of which is a separate calculation. But with the line, it's not going to make any difference, right? Our answer is because the line is going to treat a forward step and a backward step equally, and it kind of averages the two out, doesn't it? Right? The forward step on the line is a little bit less than it would be in reality, and the backward step is a little bit more than it would be in reality, but it averages the two out. And so when we get this number, this plus or minus 3/70, that's pretty nice. It's in between the two, the two real calculations that we would do if we wanted exact measurements. Make sense? Okay. It is an approximation. It's not perfect, but it's quick and it's pretty accurate. Okay. So try one of these on your own here. I want you to try this guy. Let's calculate if we're measuring. We've got this cube, and we've measured the side length of the cube to be 10.1 centimeters, plus or minus 0.1 centimeters. Tell me what the relative error is in that propagated error is in that calculation of, say, of volume. Okay. All right, so talking through this, what do we do here? Oops! Oh, that's not what I want.
It's gonna make it easy.
What did I just do? Gosh. There we go. Okay, so yeah, what do we do here? Okay, good. So we know V of x is x cubed, right? So what's dV? So, well, I'll tell you what, let's hold off on that for a second. What's V prime of x? How about? Right. So then dV must equal, as a formula in this case, dV must equal V prime of x, good, times dx, okay? Right? Okay, so now if I want to find the relative error, propagated error here, right, what I'm really trying to find is dV over V, right? And that's going to equal 3x squared dx over, what's volume?
Over 10.
X cubed. Okay, make sense?
Yeah.
Okay, and so this is pretty simple. Then I can just cancel the x squareds, and I just get 3 dx over x. And so I'm going to get pretty simple numbers here. 3 times plus or minus, what do we say, 0.1 over 10.1. Okay, so plus or minus 0.03 over 10.1, so that's the same thing as saying plus or minus 3 over 1,010. Okay. And so what is that as a decimal?
It's divided by
101. If I move it over 1, 2 places.
No, it should be
Yeah.
0.3 instead of 0.0.
Oh.
Point there, yeah, 0.3 instead of 0.0.
Oh, it should be 0.3 up there? Oh, yeah, whoops, you're right. Okay, you're right. So, I gotta, there we go. So that's gonna be, that's just about 3, isn't it? What is that? 0.0, yeah. Whoops. 0.0297 if I go out to 3 places.
Yeah.
0.0927.
0.0297? So that's roughly equal then to what percent? Plus or minus, yeah, so 2.97%, right? So here's a great little nerdy trick I'm gonna teach you guys how. Give me a number. This will impress all your smart calculus friends at your calculus parties here. From other schools. Yeah. So give me a number that's not a huge one. Say it's less than 120. That's sort of not too far from a perfect square. 80. 27. Okay, so I'm gonna approximate the square root of 27 for you. Okay. So the square root of 27 is gonna be about 5 plus 2 tenths. So it's gonna be about 5.2. Okay, find the actual square root of 27.
1.9.
Okay. Okay, that is not hard to do. It's I'll just close on that note there. I gotta leave on a high note like George
Well, let's
Costanza.
see, you took 25 for each year, that's 5, and then 7's 2 off of that.
Yeah, exactly. And so all we're doing, this is exactly what we just did here. All we're doing is we're saying instead of a propagated error, we're gonna take a propagated difference from a convenient value. I'll show you that little trick later.
That's total calculus party trick.
Yes, that's a good one.
All you gotta do is